Welcome, ladies and gentlemen, to C3-6. If you have not watched the video, the pre-video before this link on my website, make sure you do that because I'm going to be referring to this Matryoshka doll for the rest of this glue-in, and honestly, for the next two glue-ins. 3-6 and 3-7, you can kind of consider going together, even though they're separate sections of the book, but they go together in my opinion, and you'll see perhaps why. So today, a new derivative rule, the derivative of a composite function, and we call this the chain rule or the Matryoshka doll rule. And it's obviously a beautiful day for math because I get to show that kind of creepy video of the Matryoshka doll. However, I think it's a really good visual for what's actually happening in calculus. And it's actually how Ms. Chin, my calculus teacher, explained it to us. So I steal it. So we're talking the derivative of a composite function. So with these, it's important to notice, and kind of the hard part of these problems is noticing what's inside, what's outside, what's in the middle. So we're noticing the order of operations. So that's that could be a sticking point for this. So if I look at this rule, it's the derivative of u of v of x. So holy crap, that's an alphabet soup right there. Look at all those parentheses. So it's important to notice that x is inside v. So x is inside v, so it's v of x, and then it's important to notice that v is inside u. So v of x is inside u. It's u of v of x. So v of x is inside u, and then it's important to notice that u is outside. So that's the outside function, and then x is deep inside. It's the inside doll. V of x is kind of like the middle, and then u is the big outside doll in that Matryoshka doll video. So u is outside, so we're looking at the derivative of u of v of x. So let's take the derivative. Here's the rule. So we want to look at the outside function, so outside is u. U is outside, so we take the derivative of that, u prime of x, and then leave that inside doll alone. Leave it alone. There's v of x inside of u. But then, like the video, the next doll pops out. So v of x is the next doll. It pops out, and we take the derivative of that. Leave the inside doll alone, x. And then x is the inside doll now. That pops out also, and we take the derivative of x. But dx over dx is just 1, so that just cancels to be 1. So like the Matryoshka doll video, we always have the outer doll. We crack that open, take the derivative of it, and then we have that inside doll. Then that inside doll pops out. We take the derivative of that, crack it open, and then there's another doll, x. But then we pop that one out, take the derivative of it. It's 1. So let's look at some examples. So number 1, y equals 3x squared plus 1 squared. So again, we need to focus on what's outside, because that's where we start. So if we look at this, we have parentheses squared. That's outside. Parentheses squared is outside. That's the outer doll. And then inside of that parentheses, 3x squared plus 1 is inside that parentheses. And then the variable inside 3x squared is x. X is most inside. So that's going to pop out last. So we want to take the derivative of it. So derivative of y with respect to x. So we take the derivative. So the rule says, okay, look for the outside thing, u of x, take the derivative of that. So in our example right here, number 1, the outermost function, the outer doll, is parentheses squared. So we take the derivative of that. So the 2 drops down, and then we subtract 1 from the exponent. So we've taken the derivative of the outside function, parentheses squared, but we leave then that inner dal alone, 3x squared plus 1. So we've taken the derivative of the outside function, u, which is going back to the rule, and then we leave that inner dal alone, v of x. But then we see out pops that next dal, just like the video. So the derivative of what was inside there, 3x squared plus 1 with respect to x. So I'm going really kind of painfully slow here. We've taken the derivative of the outside function, leave the inside alone, but then out pops the next dal, and I haven't done calculus on this yet, so we have some more work to do. So the derivative of y with respect to x, so we just rewrite, a bunch of stuff to rewrite, 3x squared plus 1 to the 1th power, and then I'm going to throw parentheses down because I'm going to take the derivative of this nasty chunk. So the derivative of 3x squared, that becomes 6x, and then that's done, derivative of 1. But then we take the derivative of what's inside this right here. We have the x, that's the variable, so out pops dx dx, and that cancels to make 1. So done with this one. This one simplifies to be dy dx equals, yeah, let's simplify that. So let's see, 6x squared plus 2 times 6x, dx becomes 1, dx over dx becomes 1, and then dy dx equals 36 x to the 3rd plus 12x. Oop, I'm off the screen. So the only reason I'm simplifying that is because when we did this in class, we had as a warm-up problem this one, and I distributed through that parentheses squared, and if you take the derivative of it using the power rule, it ends up getting 36x cubed plus 12x. However, we have a new rule, the chain rule. So let's continue with number 2. So just a bunch of examples to look at today. So we're going to consider y equals sine of x squared plus x. So it's important to notice that sine of, well, I'll move that over. That sine of blah is outside. So that's the outermost dal. Inside of that is x squared plus x. So that's inside. And then inside of this, the variable inside here is x. So x is most inside. So we know we're going to have an x pop out at the end, dx dx. So we take the derivative, dy dx. So let's see, we need to take the derivative of the outermost function, so sine of x. So the derivative of sine of x is cosine of blah. But then the rule says leave that inside dal alone, so x squared plus x, leave it alone. But then in the video it pops out, and we take the derivative of that. Oop. All right, so we've taken the derivative of the outermost function, leave the inside dal alone. Out pops that inside dal. We're going to take the derivative of that. dy dx equals cosine of x squared plus x, just rewriting that, throw parentheses down, and then the derivative of x squared is 2x, derivative of x is 1, and again we're always going to have this kind of like dx pop out, but that's just going to be 1, so no big deal there, and there's really nothing really to do here. It's a simplified, it's not going to simplify to do much. Boom. So derivative of sine of x squared plus x is this nastiness right here. Page 2. So looking at number 3, we want to find the derivative of tangent of 5 minus sine of 2t. So we want to find dy dt. So I'm going to slide over here. Well, important to notice that outside is tangent of blah. Tangent of blah is outside. And inside of tangent is 5 minus sine of 2t. And then inside that, t is the variable. And we'll notice that we're taking the derivative with respect to t. So, well, actually, we will notice that 2t is inside of sine. So 2t is inside of there. So this one looks nasty. So we take the derivative. Again, notice we're taking it with respect to t. So the derivative dy dt equals, so we take the derivative of that outermost dull, derivative of tangent, and again this should be off the top of the head. The derivative of tangent is secant squared blah. So we take the derivative of the outermost function, tangent, but then leave that inside dull alone. Leave it alone. 5 minus sine of 2t. But then, like the video, out pops that next dull. 5 minus sine of 2t. All right. So, okay, now we need to take the derivative of that. So let's see. Oh, yeah, this one's going to be nasty. Secant squared 5 minus sine of 2t. And then the derivative of 5 is 0. The derivative of sine is, so I'm going to put negative down, derivative of sine is cosine. And then blah, but leave that inside dull alone. Inside, most inside is 2t, so out pops the 2t. And we need to take the derivative of that. And continue. dy dt. This is just a bunch of rewriting. Secant squared 5 minus sine of 2t. The 0 minus that becomes negative cosine of 2t. And then the derivative of 2t is 2. So I'll throw that in the parentheses. And that's it, my friends. We've taken the derivative and we're left with, yeah, we're good. Here we go. So not much to do there for simplifying. Yeah, just leave it nasty. Just like the Tyga song. Number 4, last one right here. Let's see if I can scooch this over. So shifting gears just a little bit. Talking about the derivative of a parametric curve. And we'll remember from chapter 1, parametric curves have two different little mini functions. The x-coordinate of a parametric curve is defined by a function. The y-coordinate of a parametric curve has a separate, different little function, and the independent variable in each of those little mini functions is a t. So we plug in a t into this little x mini function, it spits out the x-coordinate, plug in a t, plug in the same t value into this y, out pops the y-coordinate, and put those together. That's a point on the graph. So, sounds kind of complicated. And it's not. Actually, the derivative here is, I would argue, you don't even need to memorize this. It just it's super clear. So the derivative of y, the derivative of dy dx is, we take the derivative of the y function, dy dt, and then we put it over the derivative of the x-coordinate function, dx dt. Oop. Creature of habit there, dx dt. So the rule is, it's dy, if you're trying to find the derivative, dy dx. The rule is, take the derivative of the y function, and then take the derivative of the x function, and put them over each other. And of course, the y is on top, the x is on the bottom, of course. So that's the rule. So I would argue you don't really need to memorize that, because it just, I don't know, makes sense. It's dy dx, the y goes on top, yeah. The x goes on the bottom, that makes sense. So let's do an application problem of that. Find the line tangent to the curve defined by, okay, we're given a parametric curve. Again, here's the x-coordinate function, here's the y-coordinate function, and okay, so find the tangent line at this point where t equals pi over 4. So remember, in order to create a tangent line, we need a bunch of information. I'm going to put this equation down right here to kind of keep our eye on the prize of what we need. We need the y-coordinate and the x-coordinate, which actually, we'll note we're given x-coordinate, y-coordinate, so that's good. But then we also need the slope. And again, one word that describes slope is derivative. So we need the derivative of this parametric curve at t equals pi over 4. So, that's what we just learned, the derivative of a parametric curve. So, in order to find the derivative, it's this actually kind of simple rule right here. So, dy dx equals, okay, so the rule says take the derivative of the y function, that goes on top. So, derivative of tangent is secant squared of t. And then the rule says on the bottom, downstairs we do the derivative of the x function, which is secant of t. This one's my favorite. Sec t tan t. So again, notice how t is the variable in there. This is so the t is the variable here. So let's see what we got here. I can simplify this. Again, we're trying to find the slope, because that's what we're missing. We have the point, we have the x-coordinate and the y-coordinate, but we're missing the slope, so we take the derivative. So, okay, I have pi over 4. I'm trying to plug that into here. This could be a non-calculator problem, folks. This is definitely a non-calculator problem. So, looking at this, I don't know what, if I couldn't do this calculation in my head, just plugging in pi over 4, pi over here, pi over 4 here, and doing that. I couldn't do that. So, I'm going to simplify this. So, sec t tan t, so because that's secant squared, what am I doing? Secant squared is not that. Secant squared, getting excited here. Sec squared, so there's two of them squared, so that is then sec t tan t. And the reason why I did that is then those cancel. And then, let's see, continue simplifying. Let's see, what else can I do? dy dx. So secant is 1 over cosine, and then I'm dividing by tangent, because this is a fraction, secant divided by tangent. Tangent is sine over cosine. Just kind of futzing around here. So dy dx, let's see, that can then flip the second one. Oops. I can flip the second one, so that's 1. Oh, look at that, I messed up. That's not cosine of x. Cosine of t. And then I can flip the second one and turn it into a multiplication problem. So cosine t over sine t. And then cosines cancel. So dy dx equals 1 over sine of t. And then don't forget, we're trying to find the slope. And we're trying to find the slope, scooch back up here, when t is pi over 4. So really, I'm trying to find what is the slope when it's pi over 4. So let's see. I'm going to plug in pi over 4. And sine of pi over 4 is root 2 over 2. Again, this is a non-calculator problem. And then we can flip that. That becomes 2 over root 2. So I'll leave that as the slope. That looks good to me. So the slope is root 2 over 2. Go back up to my original setup. That's the slope. Back up to here. So we have all the ingredients now. We start putting it together. Y minus y1 is 1. The slope that we just found is 2 over root 2. And then x minus, and then the x-coordinate that we're given is root 2. Whew! There is that tangent line. All right, ladies and gentlemen, enjoy. This is the first heavy lifting glue in. The next one, I don't know, rumor out there it's more difficult. I think it helps explain what we just did here today. So enjoy. You're ready for this assignment. Cheers.